Hello class. Today's lecture is a continuation of the kinematics analysis for rigid body. We will focus on the relative motion analysis velocity. We will learn how to calculate the translation and rotation components of velocity and apply the relative velocity analysis. Application of this motion analysis using the velocity is, for example, looking at this mechanism that comprises of a wheel and a slider block A that is moving horizontally at a velocity of VA, causing the link AB to undergo a general motion where the end of link AB is connected to a crank which rotates about an axis, meaning that link B or point B is undergoing a circular motion. Point A is undergoing translation that makes link AB undergoing general motion. So this mechanism, while it's connected, there is a relationship between the motion of the link AB and the angular velocity of link CB, and that is associated with the base point B. The base point B, as seen by A, has two components, a translation component and a rotation, as we will see later. However, if you look into it from the perspective of rotation about the link BC, then B is simply a rotation about C. Another application of the velocity analysis is the planetary gear system, which is used in almost every automobile automatic transmission, where the gear ratio can be changed by locking the gear at different ratios, leading to having different speeds. So what's the relationship between the planetary gear, which is the circumference, and smaller gear? And another way of looking into this problem is how is the omega r goes into omega s at different ratios. So this section is part of 16.5, where we want to study a link in general that is designated by 2 points A and B, and knowing that link is rigid. This link, if we assume it goes or undergo a general motion, then at instant time it will have this shape, and at time plus delta t will have a different shape, or a different orientation, or a different position, where we can define this position as a result of translation and rotation. A translation and rotation is or should be measured about something. So we can choose that the base point B has been moving from a time instant t to a time instant t plus delta t at this instant, where it caused the entire link to translate and also rotate. So this differential position movement dRB, refer the differential position of B from B to B prime, say, is related to the movement of point A, where if you look into this vector analysis, or if we're going to apply a common sense, what happened is the differential displacement of point B due to both rotation and translation is equal to the translation of point A plus the rotation of point A, or in more vector representation, drB, the position of point B, is equal to the translation of point A plus the translation of point B relative to A due to rotation. So once you take the derivative of that equation, you'll end up with that the velocity of the base point B is equal to the velocity of point A plus the relative velocity of point B relative to A. Now we said that velocity of A is simple translation and velocity of B is the general motion, which is due to translation and rotation. And we said also that the velocity of B relative to A is simply, or velocity of B relative to A is simply the rotation of this link. Now, we all assume that the counterclockwise is a positive and clockwise is a negative. Now, the relative motion due to pure rotation, which is VB relative to A, as we mentioned in the past, is a pure rotation is an example of a rotation about a fixed point. That fixed point in this problem is looking at the B rotating about A. So if you consider A is a fixed and B is rotating about it, then the VB relative to A is simply the angular velocity cross product of the vector V or the vector RB relative to A. And that's again what we discussed about the rotation about a point. So simply, because W for 2D planar motion is in a K direction, and RBA is going to be depending on a Cartesian coordinate system if you're using it, X and Y, that's going to produce a vector perpendicular to these two. Let's re-examine the velocity or relative motion analysis using velocity using this mechanism. This is a piston being reciprocating left and right depending on the input provided to link CB. Link CB is fixed at point C and rotates counterclockwise, and that is given by the angular velocity BC. And also point B, which is connected to link CB, is connecting to the piston A through the link AB. Now, two things we need to notice. The link BC is undergoing circular motion. Therefore, point B is following a circular path. Also, notice that point A is reciprocating, meaning it's, if we decide that the Cartesian coordinate system is to be used, then it's going to take an x-axis if I assume that horizontal is in direction of x. So point A reciprocate left or right in x direction. Point B is circular, so therefore the link AB undergoing a general motion, meaning it has translation and rotation. However, link CB is purely rotation about a fixed point C. Now, if we choose B to be the base, meaning I want to analyze the velocity of that point as seen by the link CB and also as seen by the link AB. If we consider first this portion, A, B, as the link that we are examining, where we examine the velocity of B. Using this link, then I can say that the velocity of point B is equal to the velocity of A plus the rotation component that is caused by the angular velocity of AB cross product of how I am seeing B relative to A, RBA, cross R, the position of B relative to A. Now, this is true, will give you an equation. Now, because this equation lack of knowledge of VA, probably we don't know W, we will know geometry, we need more information. We need another equation, which is provided from the link BC. Now, in the same manner, velocity of B can be equal to velocity of C plus omega. Omega this time is not this omega, it's going to be omega angular velocity of link BC cross B as seen by C. Now notice that the velocity of C, which is translation, is 0. Therefore, I can say that velocity of B also equal in the left side, or another equation here, equal to RB relative to C, omega BC cross RB relative to C. So this way, I have provided an input to my equation, and I have two equations with two unknown, and I can solve them. And these two unknown could be, and this problem could be VA, which we already know its direction. We don't, because we know it's going left and right, so it has one component of unknown, right? And this is our vector analysis, and also omega of AB, which is unknown, how it's rotating, right? Let's take another example. A wheel rolling on the ground without slipping. Without slipping means it doesn't slide, meaning at the contact, point A, the velocity of the ground and the velocity of the wheel at this point are equal, meaning the velocity of ground is not moving, and because it's establishing a contact without slippage, then the velocity measured on the wheel at that contact is equal to 0. Now, to use the relative motion analysis velocity, we can choose B as a base, and we want to calculate the velocity of B as seen by A plus the angular velocity omega cross the position of B as seen from A, right? Then because VA is 0, then this is going to give us simply that the velocity of B is simply W, which we know it's, if this is 2D problem, is so it's going to be WK cross RBA RB as seen by A. So its vector is going this way. It's going to give us a linear translation of B as expected. So let's look into the analysis procedures. There's different ways to solve a problem. You can either use the scalar analysis method or the vector analysis method. Well, in both cases, I recommend to use the vector analysis method simply because you want to eliminate any error in making and not make assumption. But if the problem is too easy, then you can follow that. And what it does is first, before you start solving, establish a proper coordinate system. Most commonly we use XY coordinate Cartesian coordinate system, where you will draw the kinematic for the body and also label the magnitude and direction of the relative velocity for both the known and unknown, including the relative velocity vector. And then write the relative velocity vector equation that relates the base function or the base velocity to a point on the link, or one link or another link, depending on how many links. And knowing that you take care of any additional information known about the motion of these points, and then solve for the unknowns. It's kind of more obvious when you do the vector analysis, where you write that equation and you label the vector components and with their direction in I and j. And if the assumption for the angular velocity tends to be opposite to what you assumed in the first sketch, then meaning that you have chosen the opposite if the result is negative. And then you say that the orientation of the angular velocity is opposite. Let's take an example and make it more clear. Consider this roller, which is sliding over a wall. A roller of that link at point A is translating to the right at a given magnitude, 3 meters per second. So we know the velocity vector, which is, if we choose that the Cartesian coordinate system for this mechanism is to be positive x to the right and positive y to the upward, then the VA equal 3I. This is a vector. And also we know, because the B point is rolling downward, we can assume that the VB is equal to negative VBG, or VBJ, where that indicate the VB indicate the magnitude, and negative J means it's going downward. Okay, so what is given to us is the base A, or the velocity of point A, translation A. We want to find the angular velocity of the link AB at an instant 30 degree. Okay, so the first thing is draw the kinematic diagram. If this is going to the right, A, then yes, we definitely can say that VB is going to the downward as a result of rotation of link BA counterclockwise. Now, can label that as an omega, and this omega is unknown to us, so it's omega k if we're using the vector analysis. VB, we can say it's has a magnitude of VD negative J, and VA we said it's 3I. Now, the relationship between A and B simply can be established by examining B as a base point, or if you want to do the other way, it doesn't matter. But since we know already the information about A, it's easier to say, okay, I know the direction of B, so VB, which is negative BJ, equal to the translation of A plus the rotation about point A, right? Assuming that's a combined motion, which this motion is simply the VB relative to A is equal to omega cross RB relative to A. So omega is omega k. This is as a vector, this is as a magnitude, so this is, red means a vector. This is all as a magnitude, omega cross product of R, B relative to A. So RB relative to A, meaning I'm drawing a vector that has a tail on A and head on B. So this vector is simply has two components, cosine 30, 1.5 going to the left, so the negative 1.5 cosine 30i, and a component j upward, 1.5 sine 30j. Now this cross product, so to do the cross product operation, going back to the so to perform the cross product between omega k cross that vector, you distribute. So first of all, the scalar quantity goes outside, and the vector use this right hand tool or right hand rule. So omega multiplied by negative 1.5 cosine 30 multiplied by k cross I. So we have a k cross I, so it's a positive orientation, is going to produce a positive j. So that's a j. Now you distribute omega k over the second portion. So it's going to be omega 1.5 sine 30 k cross j, k cross j. So that's going to be in negative, so it's going to produce an I. So it's going to be a negative I. That's a negative I. Okay, so that's how you do that. So and then you'll end up with this equation. So summing the i's together and j's together, you will end up with an equation with two sides. A side in the left has a negative bj. You compare that with the j in the right side. So you have first equation negative b equal to that negative 1.99 omega. And the second equation you extract from this vector is by comparing the I component. Nothing in the left, zeros, equal to 3 plus or 3 negative 1 point or minus 1, sorry, minus 0.75 omega. So we have in the first equation you obtain omega, and then you substitute that value on the second to obtain the dB. That's going to give you omega equal rad 4 rad radian per second. And that's going to be in k, because we know it's in k. And dB, we know it's going downward in j. That's the velocity. Okay. We have a problem that involves a crank OA rotates about a fixed point O that causes a link AB to push a piston in upward or downward direction depending on the position. What we wanted to find is the velocity of the piston B and the angular velocity of link AB at this instant 30, right? So we know that the velocity of B is equal to, or is going upward or downward. Well, as this is going, rotating more to the counterclockwise, we expect this to go upward, probably. Now we can assume that the velocity of B is a magnitude VB on J, assuming that J positive is upward and I positive is to the right. Okay, so analyzing the velocity of B from this link is equal to velocity of A translating plus the relative velocity of B as seen by A, which is equal to the angular velocity of link AB cross product of B as seen by A. So the vector is going downward like that. The head is here and the tail is here. Now, another level to analyze this problem is that we know velocity A. Velocity A in fact is rotating about a circular path because it's connected to link AO. Therefore, velocity of A at that instant is tangent, right? Tangent. And anyway, if you don't like it this way, you can just put that in a vector where it's equal to omega AO cross the position of A as seen by O. Okay. So putting that into schematic, that's what you're gonna get. Now, this is RB with respect to A. That is the velocity of B, assuming it's positive upward. That is velocity of A. You didn't have to assume, it just the cross product will generate that VA to the left. So velocity of B, which is assumed as a component VB, is the magnitude by J, is equal to velocity of A, which we know it is has a two component. It's 0.3 velocity of A so velocity of A can be analyzed again from link AO using the relative analysis. We can say that velocity of A equal to velocity of O plus the angular velocity of AO cross RAO. Now velocity of O is 0. The angular velocity of link OA is given 12k cross the position of A as seen by O, which is that vector, so it's 0.3j pointing upward. So 12 by 0.3 is 0.36. Oh, sorry, it's a 3.6. 3.6. Now k cross j, it's going counterclockwise or clockwise, right? And producing an I, so it's a negative. So negative I. That's what visually you can say using scalar method. So I would prefer you using this. It's much consistent. So VA is unknown, so you plug in VA here and you do this cross product using the right hand rule, and this will end up to a vector equation where you isolate j's and i's and two separate equations where you equate the i's and the j's separately, and that will lead to two equations. First, the i's 0 equal to negative 3.6 plus 0.3 w, and the j's is the VB equal to j's in here, and that will lead to solution of given here, and they are positive, mean our assumption is correct. So with this example, we finish this exercise or this section. There is others you can try, concept and group problem solving. And I'll see you guys next lecture.